All right, so I'm switching gears and going to the board now, and we'll come back to slides in the end. And of course, I encourage you to stop and ask questions. So I'm going to go through this old school lecture style. We're going to start from the beginning and work our way up to the end. We heard about T-mu this morning. I'm going to focus on a kinetic theory picture in order to have some grounding here. And in kinetic theory, I can obtain T-mu by integrating over the invariant phase space measure. The invariant phase space measure is defined over here. It's a three-dimensional integral over momentum divided by 1 over p dot u. U is the forward velocity of the local rest frame. So that's telling us how fast the local medium is moving collectively. If the fluid is at rest, a static fluid, then this is simply 1, 0, 0, 0. It's normalized to 1, as Francesco pointed out this morning, always because it's a forward velocity. And if it's static, it's just 1, 0, 0. And in the local rest frame of the matter, so let's imagine the fluid was all flowing to the left, and I boosted myself into that frame so that I was flowing exactly with the fluid. So in my frame now, it looks like it's not moving at all. It looks static, right? So this is also when I boost into the local rest frame of the fluid. And in that case, in the local rest frame, and I'll use this LRF to save myself lots of chalk as we go, this special combination 1 over p dot u just reduces to 1 over p naught, or 1 over the energy. And you might recognize this maybe from quantum mechanics class when you're quantizing theories. It's a Lorentz invariant phase space measure, right? So it doesn't matter what frame I'm in, this is always the same. It comes from a 4-dimensional phase space integral to begin with a delta function that enforces that the particles are on shell, and a theta function that says that they have positive energies. But I won't write it anymore, I'm just going to write dp. So again, to save chalk everywhere. So T-mu in this case is defined as the following integral. This is the one particle distribution function. I'm going to, again, tie myself to kinetic theory, but a lot of what I'm going to say after this, is independent of that. But because we're eventually going to need to get a distribution function out in the end in order to convert things back into particles, I find it useful to think in this way. Now, let's look at some specific components. T00 is, and I'm just going to look in the local reference frame to begin with to keep my life simple. That's P0 quantity squared times F of P. Let's expand that out. I said I wasn't going to do it, but I have to do it for this example. I had a P naught squared on the top. I have a P naught in the bottom. This is the probability of having a particle with momentum P. This is its energy. This is nothing but the energy density. So this is the average energy, otherwise known as the energy density. Likewise, if I look at any of the space-like components, again, let's look in the local reference frame. It's the same integration measure here. These will just be the pressures in the different directions, measured in the local reference frame. Now this thing is a 4-vector, right? You have to be careful, but as we're going to see, these quantities play a special role. Now, if the system is perfectly isotropic, then this thing is only a function of the length of P. And then all three of these integrals should be exactly the same. And then Px is Py is Pz, right, by symmetry, because the probability doesn't depend on which direction I'm looking in. All right, so that's just some setup. All right, T mu nu, as we can tell from its definition up above, is a symmetric tensor. It starts out as a 4x4 matrix, right, which has 16 independent components, but because it's 10, because it's symmetric, these 16 go down to 10 independent components, right? We heard this 10 this morning already. Now, we're going to focus first on ideal isotropic system, because I don't like to do the hardest thing first. So how do we write down T mu nu in general? So we saw Francesco's complicated version, which was correct. I checked. We're going to start slower. How do we approach this problem? We have a symmetric rank 2 tensor. What are the components that we can build it from? In this case, we only have the fluid 4 velocity and the metric tensor itself. So those are the only two things, only vectors we have at our disposal in the ideal isotropic system. There's no special direction of space or anything like that. So those are the only things I can build T mu nu from. So what this tells me is that I can immediately write down, let me make sure I define the general energy momentum tensor, no matter what, in the following form as a bilinear, because I need two indices over here in u mu, and then the metric tensor, it already has two indices. And that's the general form, and I'm done. That's the end of the lecture. No, it's not the end of the lecture. So what are these coefficients? Well, the nice thing about doing the expansion this way is that these coefficients, A and B, are Lorentz invariants, right? So I can write it in this form. This thing is a tensor. It depends on what frame I am in, but I can extract these coefficients here, A and B, in a Lorentz invariant manner. So Francesco showed us how you might go about doing that. Let's look at one case. So if I come in with this vector u mu and I hit T mu nu, I get that. Agreed? If I hit it with another one, let's just do it, u nu, project out both indices, then this simply becomes A plus B. Right, so that tells us that from this Lorentz invariant quantity, because it's got fully contracted indices, I know what A plus B is already. Now, in order to get, I need another equation to completely fix what A and B are. So I'm going to introduce another symbol that we already saw this morning, which is this transverse projector. The transverse projector is defined as G mu nu minus u mu u nu. What this transverse projector does is it takes vectors and it projects components that are orthogonal to the local fluid 4 velocity. So you give me a vector, and this is the local fluid 4 velocity, it just gives me the component orthogonal to it. In the local rest frame, what does this thing look like? I should tell you what is my G mu nu convention. It's the same as Francesco's. Thank God, I was really worried about that in the morning. It's the mostly minus convention. In the local rest frame, this is just that tensor over there, and u mu u nu in the local reference frame, this is just 1, 1 in the 0, 0 component. So this just becomes 0, minus 1, minus 1, minus 1, with zeros off the diagonal. Now the nice thing about this projector is that if I come in with a u nu rather, let's do down here. Here, this is going to just become u nu, and u mu times u mu is 1. U nu, this thing is 0. Of course, we kind of knew that from the definition in words, because the components of u orthogonal to itself are 0, right? So it's by definition 0. Good. Now, some other nice properties of this projector which we'll make use of, and it doesn't matter if I project from the left or the right. I think you can convince yourself of that pretty quickly. Another nice property is that if I take products of these things, I just get back another projector. So that's the definition of a projector, right? If I project twice, I just get back. So that's what makes it a nice quantity. Good. I'm not used to this flying board thing. So we established one equation already, which was that u mu, t mu nu, u nu was equal to a plus b. And now what I'm going to do is project in the following way. Instead of with 2 u's, I'm going to project with 2 of these orthogonal projectors, transverse projectors. Based on this original assumption that was sitting here, when I come in here with a delta, it's just going to be the contraction of 2 of those deltas. It's just going to give me a delta back by this rule. Deltas hitting this term are going to be 0 by construction, right? So this is just going to return A times delta AB, another transverse projector. Make sure I didn't screw up any. Oops, they should be up. Sorry. Yes. Mu nu up. Thank you. Good. I did it differently in the notes. That's okay. All right. So now what we're going to do is, because these things are Lorentz invariant statements, right? Again, I've contracted all indices here. I've contracted all indices here. I can now start working in the local reference frame to keep my life simple. So let's do that. And the only thing I've done here is to restrict to these 3 space-like components, because this one is 0. So there's one part of this one that just says 0 equals 0, right? If I take mu and or nu equal to 0 in the local reference frame, this is 0, that's 0, trivial equation. So these are the 3 non-trivial equations that emerge from that, at least in the local reference frame. And now we can ask, what is this quantity? In practice, going back to that expression up there, and if you do the math, well, I don't want to move it too much, you'll find that this is simply dp pi pj f of p, which in general are these, if I was equal to j, these are the pressures. In general, it's something else. Since we're doing ideal hydro, we're going to assume that this thing only depends on length of p, If it only depends on length of P, any of these integrals where I have one, like Px, Py, it vanishes by symmetry, right? If I have Px, Px, that's going to be non-zero, right? Because even integral, even, any of the rest of them are odd. So this will become minus delta Ij times the pressure in the ith direction. Let's just write it that way to begin with, but since it's isotropic, the pressure will be the same in all directions. So the fact that this only depends on the length of P is the reason you get this Kronecker delta here. Now, as we go away from equilibrium, you have to be careful at this step that this might not happen, but we're starting with ideals, so this happens. So this thing we just proved was just delta Ij times P. And that gives us our second equation, that A is nothing but the pressure. Minus the pressure. What did I screw up here? No, there's no minus. Thank you. Thank you. This is what happens when you get too close to the board. Thank you. All right, so the only thing I have left to do is put these two equations together. The other piece of information I need is what is this written in terms of quantities in the local reference frame. So let's use our our kinetic theory translation for this. It would be integral dp. Then I would have p mu, p nu, and this would be a p naught squared in the local reference frame times F, and again, we're assuming for now that this thing is perfectly isotropic. That's nothing but the energy density. So we have two equations now that A plus B is equal to the energy density, and A was equal to minus pressure, and this all has to go into our starting expression. Good. And I'll start putting an ideal on this to emphasize that we've made a bunch of assumptions here along the way. So of course, from this, anybody can show that B is just the energy density plus the pressure. And then turns out that I can write T mu nu ideal in one of two forms. And you'll see different ways of writing this in the literature. So don't get upset if it's not your favorite way. I like the second way. I'm getting ready to write it better. Okay. So that's it. Now again, the nice thing about writing it this way is we started with a sort of general statement that we just have a rank 2 symmetric tensor to decompose. We have certain tensors and vectors at our disposal. This is the most general way you can write it. We could have stopped here, right, and just run with A and B, but now we've tied it to some physical quantities that this is the energy density in the local reference frame, and this is the pressure in the local reference frame. Good. Now, if we look in the local reference frame, this simply has the following structure, where I just have the energy density in the 0, 0 component and pressures along the diagonal that are equal. Right. Good. Now, continuing with this assumption, we now want to apply a rule that's sacrosanct to physics, namely energy and momentum conservation, right? So we now want to rewrite this as a set of partial differential equations, which we could then potentially throw into a computer by requiring that the following is true. But this is not a Lorentz covariant equation. There's 4 of them hiding there. I'm going to ignore the number conservation equation to keep things simple. And we're just going to focus just on energy conservation. But you can do the same thing as Francesco pointed out with the number density. We'll see that in the future. It's just a vector, so it can only have u and then some component that's orthogonal to u. Let's focus on this. All right, I want to show you how you then translate this out into the standard form that people write hydro equations in. So the only thing we have to do is plug in this general form here and start applying the chain rule repeatedly. And I'll try to stick to a notation that the derivative always acts only on the things in parentheses to its right. And I'll make it even more explicit by doing that, just so that nobody gets confused. What did I do here? I just went ahead and wrote that like that. Oh, that's because I was using this form, which is easier to deal with. Sorry. Yeah. Sorry, start with this one. It's easier for this manipulation. Don't do that one, although it's more beautiful. So here I took, and I reversed the order. So I took the derivative of this, then I took the derivative of these two guys, and then the last term is just the derivative here. Yeah. Okay, sorry for my confusion. Right, so this thing is 4 equations, and it depends on nu everywhere as the dangling index. So now I can project with u. So this u hitting this guy is just 1, so I get rid of it. And I've just pulled this u over to the left to bring it on the outside here. It's not inside the derivative, I just pulled it over. And I'm going to call this a special symbol. Some people write it simply as a dot. It's the co-moving derivative. It's the derivative along the direction of the flow. Yeah, so it's projected with u. So it's the derivative in the direction of the fluid flow, which is called the co-moving derivative. So I'm going to write that as capital D. Good. Then I come into this term. And once again, u mu is going to turn into 1 here. And this special quantity here, the forward divergence of the fluid flow, in order to keep the things compact, this is defined as theta. So that's going to become a theta in our notation. And then finally, this term This one Francesco discussed earlier. This turns out to be 0 because I can rewrite this as that. But this is just 1, so that's 0. So that term goes away, that's nice. And then finally this term here with the u nu, this just becomes another co-moving derivative. So I get another plus dp. So this term is gone, thank God. I didn't like it. Yes? Did I mess something up? Minus, thank you. I would eventually paid the price for that, thank you. But if you would have allowed me to make the earlier mistake and then I would have corrected it, then through a second mistake, then thank you. So with that, I can write that the first equation that I got from projecting with u mu as the following simple looking equation. Now there's 3 more equations hiding. And to get them, I'm going to project with delta alpha nu, so the transverse projector instead of u. So which form did I use? Looks like I used this one again. Did I? Yes, maybe. What the hell did I do here? Oh, I have to project that equation up there. That's what confusing me. All right, so I have to project that equation that's hiding up there on the very top board with one of these guys. So a delta, I need the long stick now. This delta will hit this guy and go to 0, right? So the first term is going to be 0. Then the next term is going to be epsilon plus p times delta du. So let's write it out. I used the fact that this, came from here. This one was 0. One of them was 0. Yeah. This is just d. This one was 0 because delta coming in just latches to that guy. It's orthogonal, so it goes away, and you just get left with that. Good. And then the final one is when the delta comes in here, and that's given a special symbol of a knob. Where the nobble is simply defined as the transverse projector hitting a normal derivative. This one I called D. Yeah, sorry. This one I just called D. Trying to keep the notation from exploding, but it can be confusing. And because I won't show you every detail, I want to get the symbols down first so that when you look in the literature, you'll be able to read it. Good. And of course, this should all be equal to 0, right? The 0 over here. Because it came from d mu, t mu nu is equal to 0. Good. So we have to work out what is this. And for that, once again, we're going to use some sort of trick to rewrite it. Of course, the co-moving derivative, or any derivative of this, is zero because this thing is zero by itself, but I can then apply the chain rule that d applied to this plus d applied to u is zero, and I can just reverse the order of these things. Turns out to be the easiest way to do this. And then the only thing you have to do is expand out this derivative that's sitting here. So what is delta alpha? We lost it. It was hiding up here. I have to evaluate a derivative of this. Of course, my local metric is that nice flat one. So I'm working in Minkowski space. If you were in a curved space, you should be careful now. But in Minkowski space, this is zero. And then I get a derivative of one of these guys. So in the end, this whole thing just becomes, if I did the math right, derivative of u alpha good. All right, let's put a box on this one. All right, so there was a zero. This whole thing became du alpha. And then in this case, I'm going, because I want the three other equations, I'm only going to consider the case that alpha is space-like. Again, if you want to think in the local reference frame, this thing only has non-zero components in the three space-like directions. So in the local reference frame, it really makes sense to think of alpha as I, 1, 2, 3. Yeah? So in the end, this translates into epsilon plus p, derivative of the fluid, co-moving derivative of the fluid floor velocity, gradients of the pressure along the space-like directions has to be equal to 0. And this is three equations. This is one equation. So this came from projecting with u mu, and this came with u rather, delta alpha mu. So expressed in this way, these are now the partial differential equations I need to solve in order to evolve ideal hydrodynamics. As we're going to see, I don't have quite enough information here to actually evolve things because I only have 4 equations, right? I have 1, 2, 3, 4 equations. How many unknowns do I have here? I have the energy density, I have the pressure, and then I have 3 components of ui that I need to evolve. So there's 5 unknowns floating around here. And Francesco covered. Yeah, so that's how we close it now, is we invoke the equation of state, which is a relation between epsilon and p. So I can rewrite p as a function of epsilon, or epsilon as a function of p, and then I close the system of equation. But here I need an equation of state. And that's why traditionally people in hydro will say, well, I have to be in thermal equilibrium because I need an equilibrium equation of state at this point in time. And it turns out you can relax this assumption a little bit. You don't need to be in equilibrium. You can still provide a kind of equation of state, even out of equilibrium, but that's traditionally where all this came from. This idea that you had to be in equilibrium came at this point. We had to apply equation of state. There has to be some relation between energy density and pressure. Now, formally, this comes from the trace of T mu nu, which is something called the interaction measure, and it can depend on T, and this you can do in your, from the general expression above, it's just energy density minus 3 times P. In a conformal system, the energy momentum tensor trace is 0, the interaction measure is 0, and then E is equal to 3P. Now, this statement is independent of thermodynamics, actually. It would happen even out of equilibrium. Any conformal system has to have E is equal to 3P. So that's a general statement. So when you start dealing with conformal systems, you start to realize, I actually don't need like a thermodynamic equation of state. I just need some constraint that exists in the theory. And in conformal systems, it's this that comes from just having massless particles around. Good. Now, if that's the case, which we're going to focus on for a little while, because again, I want to keep things simple, then we can rewrite these two equations up here. Wherever I see the pressure, I can rewrite it as energy density over 3. And then I can rewrite those two equations in the following form. Okay. So now everything's closed. I have 3 independent variables with the flow velocities, and 1, which is the energy density, 4 equations, everything's good. I can solve that. I just put it on a computer and I solve it. The first equation, remember this thing, theta, is the forward divergence of the fluid flow. It's telling us how the energy density responds to gradients in the fluid flow. And the bottom is telling us how the fluid flow responds to gradients in the energy density. And then we close it, and then we solve it as a function of time. Now I want to simplify it further, and when I'm done with that, I think we'll be done for today. And then we'll pick up finishing lecture 1 tomorrow. These are the ideal hydro equations. They're not reality. We're going to see. Once we start going to non-ideal case, it'll explode. But I want to teach you the basic methods for getting anywhere. Where this seems like a good board to erase. So the final thing I want to get for you today is a sort of standard solution that everybody in heavy ion uses and throws around, which is called the Bjorken solution. So the Bjorken solution comes from these sets of equations and an additional set of assumptions. Namely, that my flow has 2 things. 1, all variables, there's only depend on something called the longitudinal proper time. They don't depend on the transverse coordinates at all, and they don't depend on eta. So in terms of our space-time diagram, this is T, this is Z, it's our light cone. We can draw hyperbola corresponding to fixed proper times. And then there's an angle, right, which we can introduce, which is the space-time rapidity. Now don't confuse this with the shear viscosity. I know it's confusing, but people use the same notation for it. This is just, when eta goes to 0, you're here, and eta is infinity, you're riding along the light cone. So in the Bjorken model, you assume that variables only depend on tau, but not on eta. So on any any hyperbola here, things are a constant. Yeah, that's the assumption. So I don't show the transverse directions. We're going to assume that the energy density also doesn't have any derivatives in the transverse direction. So this is, imagine a nucleus that's infinite in size in the longitudinal direction, so that the gradients are, super small, and I'm looking here in the middle of this giant thing, this is a good approximation. And because there's no gradients in the transverse direction, there will be no flows in the transverse direction, right? Because flows only develop, as we know from this equation, in response to gradients in the energy density. So as long as I set that up, I can ignore the transverse directions. Now I want to go from here and now implement the next constraint, is that variables don't depend on this boost angle and only depend on the longitudinal proper time. And the way to do that is to map to what's called Milnor coordinates. So instead of solving the problem in t and z, I'm going to use tau and eta as my coordinates. Yeah? So I'm going to use these new variables. And in this new set of coordinates, I can calculate the metric tensor in the following way. That's an alpha. Where now if it's a tensor, or at least in this next short bit of the lecture, if it's a tensor in Milnor space or a vector in Milnor space, I'm going to put a hat over it just to emphasize. And this is how I make the coordinate transformation between Minkowski space and Milnor space. So I just have to take derivatives of t with respect to tau or z with respect to eta and work out the math here. And then I can get the metric tensor in Milnor coordinates. And I'll leave that as an exercise for you guys. That when you get done with that exercise, you'll still have a diagonal metric tensor, but it'll be 1 minus 1 minus 1 minus 1 over tau squared. If you, sorry, probably can't, I don't know if you can read that. It's in the notes. So that's just some algebra between, and a little tiny bit of calculus between you and the answer. This is with upper indices. If you do lower indices, this becomes a tau squared instead of 1 over tau squared. I think I got it right, but I'm always unsure about this. I always have to double check myself, but I think I got it right. But if you find that I got it wrong, please let me know, and I'll fix the notes. Okay. So we now know how to write the metric tensor in Milnor coordinates. We also want to write the fluid velocity in Milnor coordinates. And there's a special kind of flow that will map to a static flow in this Milnor coordinates. And a static flow in Milnor coordinates means that if I go onto one of these hypersurfaces and I go to any point on this thing, U will be static, which means it'll be 1, 0, 0, 0. And that particular flow that does that is one that looks like this. And it's not so obvious if you write it in back in terms of z and tau, right? That thing will somehow magically result in a static flow in the local reference frame, and it's got some complicated dependence on z and t down here. But when you write it in this way, it's kind of obvious that it is going to result in a static flow because this is nothing but a Lorentz boost by eta of some static flow vector, right? Remember, a Lorentz boost has cosh, sinh, cosh in the corners, and this is along the z direction. So if I do a Lorentz boost of this static vector, I get this in the lab frame. This is what it will look like in the local reference frame. So that's how you know that this is going to be the special combination that's going to result in something simple in Milnor coordinates. Okay, so this is just a boosted static flow. Once we have this explicit form for u mu, we can, in whatever coordinate system you prefer, we can evaluate the four divergence. We're going to need that in the equation that I erased. God, I erased it. Was this guy here. I'm going to need, oh, that guy up there. Sorry, I'm going to need theta up there in equation 1. So I need to evaluate this. So you can do it either way. You can do it explicitly in terms of t and z and take derivatives of this guy, or write it in terms of tau and eta. That's up to you. You will find, irregardless, because it's Lorentz invariant and coordinate invariant, that that's just 1 over tau in this special case. Likewise, just to complete the coordinate transformation, you can write the fluid flow velocity now in Milnor coordinates. Things with hats are in the Milnor coordinates. Again, you just have to take some derivatives of the defining relations, which there they are, of these things, or the inversion, which writes tau and eta in terms of t and z. And what you'll find is that this comes out to be as advertised, 1, 0, 0, 0. And what's important here is the last component, u eta, is 0. Now we already made these first two explicitly 0 just by assuming that the thing was transversely homogeneous. But in the lab frame, this thing has both, it has some z velocity going on. But if we boost into the local rest frame of the fluid with this particular fluid velocity, we find that it becomes a static flow. So that's going to simplify our lives a lot. Sorry, yeah, I wrote something wrong here. Thank you. This should be alpha. Yeah, it's wrong in the notes. Thank you. Thank you. Thank you. Thanks. The nice thing about this being a static flow is that if I come in with, and I write this now in Milnor coordinates, remember I have to figure out what this co-moving derivative operator is in whatever coordinate system I'm using. because this thing in that coordinate system is just 1, 0, 0, 0, 0, this just becomes a derivative with respect to proper time. And now we can plug in everything that we've just learned, namely that theta is 1 over tau, d just reduces to a proper time derivative into these two equations up there. That'll be done. All right, so equation number 1 for Bjorken flow. Becomes simply proper time derivative of the energy density plus, remember we had the simplification that for the, and I'm going to, should be conformal Bjorken flow. I imposed my conformal equation of state. So it was epsilon and then 1 over tau, and that has to be 0. And then this equation, this becomes a normal time derivative, but in Milnor coordinates, all the 3 space-like components of these are 0. So ux, uy, u eta are 0. And the gradients xy are 0 because I assumed that from the beginning. But in Milnor coordinates is also independent of eta, which is now, this becomes gradient with respect to eta, so that's 0. So the second equation simply becomes 0 is equal to 0. So good. So that's Bjorken flow. Turns out in the conformal case, we can solve it analytically, right? This is a very simple, ordinary differential equation now because this thing only depends on, this really is just a normal derivative with respect to proper time now. I can just solve it. And the solution is that the energy density is equal to some initial value, tau naught over tau to the power 4/3. And in a conformal system, the energy density can always be written as a number times the temperature to the power 4. So once I know the energy density evolution equation, I know what the temperature evolution equation is. So this then tells me that the temperature is T naught, tau naught over tau to the 1/3. Now this 4/3, it came from here, right? It came directly from there and was related to the fact that I had a conformal equation of state. But this now tells me that temperature evolution under a large set of assumptions, but it sort of forms the baseline for everything to come. Once you know how to derive these equations, you can get the more complicated ones that you have to do with a computer. And what we see is that the temperature will drop as a function of proper time as we go forward along these hyperbola as tau to the 1/3. If I set tau to tau naught, I get my initial condition back as I expected. Now, you could have had a massive gas with, say, a constant speed of sound instead of a conformal equation of state, and the same kind of formulas. So if it was a massive gas, with, instead of E is equal to 3P, E is equal, let's call NP here. Now, typically, we write the speed of sound, right, is CS squared is dP dE. So on the left, this gives us 1/3 speed of sound. It's a conformal system. In general, you'll just get CS squared is equal to 1 over whatever that number is that's sitting there. So even for a non-conformal system with a constant speed of sound. So what generally appears up here is the speed of sound squared. Now, if the speed of sound squared depends on the local temperature and stuff, then it gets complicated. But if it's a constant speed of sound, then what appears up here is just simply the speed of sound squared. All right, I think that's a good place to stop. That was mostly to get us used to the notation and check my ability to get minus signs right. Tomorrow, what we'll do is, maybe not in such gory detail, show what happens when we start adding the viscous corrections and how do we get the equations of motion for the viscous corrections. And just a little bit of foreshadowing, it's going to get complicated quick. Our model for tomorrow is going to be that we're going to start with this basic assumption that it's ideal, but as we've all learned as we've become adults, nothing in life is ideal. So we're going to have to add a non-ideal part, and we call that non-ideal part pi mu nu. This thing, coupled with the equation of state, this has 4 degrees of freedom, and we were able to get 4 equations of motion for them. This guy, because T mu nu generally has 10 degrees of freedom, it has 6 degrees of freedom hiding in it. And because of that, we're going to need 6 more partial differential equations. Once we find those 6 partial differential equations, we can evolve all of T mu nu, but not until then. And so we're going to need more information than just this conservation law. The conservation law only gave us 4 equations. So where do the other 6 equations come from? That's tomorrow. Thank you.